Okay, so thanks a lot, guys. Yeah, well, I'm starting with 5 minutes delay. It's not a problem. Let me try to share the screen. Okay, so our panel is on new learning methods, and I let the subjects on purpose very broad, right? As Professor Peters mentioned, this is something very popular nowadays, especially at the European level. And of course, I could have been more precise with the title, but I think it's better to kind of keep it broad and kind of drive some of the questions from you and to try to see if you can come up with some different ideas from our panelists regarding the new learning methods. So let me briefly introduce the panelists. I chose them also because I have different level of expertise, but also different experience. So Alberto, probably you all know, he's one of the pioneers on multimedia research, retrieval, image and video analysis, and so on. He's now the chair of SIGMM, which is the main organization behind ACM Multimedia and general the multimedia research. And he's been working on very important topics, and you will see today he has some interesting viewpoints on this subject. Then I will have my former colleague Kay Snook from University of Amsterdam. He's been a rising star for the past few years in multimedia and in computer vision. He is leading now a very successful group at the University of Amsterdam, and he's looking quite a lot into, let's say, real life learning, which is, I think, it's quite an important aspect nowadays. Also from considering that the industry is interested directly into this type of subject. And I will finish with Radu Ionescu. He is a professor at the University of Bucharest. He's been working on many topics, not only computer vision, but also NLP and language. And I think from this point of view, it's a very good complementary expertise compared to the other two panelists. So let me start with something very, very briefly. So what we want to do during the panel is to discuss some new learning paradigms in AI. Some of the topics that I took from the abstract of the panelists. So one would be online and continuous learning. This is quite an important topic. Then we will move towards green AI. So trying to do efficient and cost-reduced approaches for this. And finally, as I mentioned, Case will cover the aspect of real-world learning, right? So trying to dynamically learn, to generalize across domain, labels, and tasks. And this is quite important, especially if you can do it in a data-efficient fashion. Okay. Let me start with a paradigm of deep learning, because this is what everybody does. This is more like it's a sort of parody that I found it quite interesting, and I'm showing it just to give you the impression that the society has about what we do, right? So society believes that whatever we do deep learning is something very cool, right? So it's more like a Terminator. Then what my friend thinks I do, okay, they don't know about anything about deep learning. They believe that my brain is connected to the computer, and that will be some sort of, kind of AI stuff. What other computer scientists think I do is that, well, I'm just a lazy guy, having a lot of money, right? And then because we are very successful and we get a lot of money. What mathematicians think we do is that like these funny guys that it's kind of trying to do the computer, trying to manipulate the computer without knowing what we're doing. What I think I do, it is, well, I am as cool as Jan LeCun and other guys, right? And in the end, what we really do, it's something very simple, right? We do some kind of simple programming, and then we can achieve also some good results. Okay, so what I put in here is that different perception of learning and different things that you could consider are important. If you look into, let's say, the market analysis, this is what PricewaterhouseCoopers came up with, let's say, the top 10 AI technologies. And if you see here, they are all related to machine learning in general, right? So deep learning theory, capture network, and so on. These are the trends, let's say, the current trends from last year, but they are more or less related to what it is right now. In my opinion, this is also my personal interest, there are a few things that are quite important. So one is to do augmented data learning. I think it's quite important in this respect. going towards generative adversarial networks. This is something that we all do, and also generation. We were discussing before in the panel about the deep fakes. And then, of course, explainable AI. Of course, all the others are important, but I would believe these are quite relevant. And why is it so? Well, simply because we are living even more so nowadays into a multicultural, multilingual environment. We have access of an instant access to and storage of multimedia information. So not only user created images and videos, but also information from sensors, RFID, Fitbit, and so on. We have to deal with a variety of devices, so now cell phones and everything. So deep learning and learning in general will have to be efficient to work on cell phones and so on. And then we also have to deal with different type of media, synchronized or maybe unsynchronized, so voice, video, text, and so on, for example, having different bandwidths. And we have to deal also with lower communication costs, more asynchronous collaboration, and so on. So in the end, we are living into an interacting environment, and I believe the new learning method will have to really deal with this, let's say, the fact that the user is now interacting quite a lot, and we have to accommodate for this. Okay, so these are, let's say, my introductory slides, and I will let Alberto to discuss about his viewpoint. And then, so it's about 10 minutes each, I told my panelists, and then we can have the open discussion. Alberto.
Thank you so much. I share the screen.
Yes.
So do you see that?
Yes.
Thank you so much. So thank you again, Nico, for the presentation. I will talk about some recent research we are currently doing that is about learning compatible representations, and particularly a new method that uses feature stationarity to do that. Let's introduce shortly the problem. The problem is in the framework of visual search, open set recognition. In other words, typically in a current system, deep neural network perform recognition and visual search by indexing a gallery set using some similarity metrics. But in practice, what happens in many problems of visual search or open set recognition is that new data are available and new classes are available. So you have to upgrade the recognition model. So this upgrading, typically when you use a deep neural network, requires that you re-index the images in the gallery set. In other words, you have to reprocess the entire gallery set to generate the new features. However, sometimes this is not possible, either because the former images are no more available or because of privacy constraints and so on. So one important issue is to have new features, new representations that are compatible with the old ones. So this compatibility, and we will talk about that in a while, will allow to not recompute the old features. So to keep the old features as they are and have the new features that are still compatible with the old ones. Shortly, what does it mean? Here in this image, you see what happens in a traditional deep neural network model represented in 2D. In the first image on the left, you have 5 features, and then a 6th feature is added to the 5 on the right. And you see that the geometric configuration of the former features is changed. This because addition of a new feature changes the representation. Well, compatible features are a situation where the geometric configuration does not change even though you add new features. So how do we believe we can get it in a very effective way? Very recently, there has been some research on the so-called fixed classifiers. Fixed classifiers are classifiers where the fully connected layer is fixed, so does not go into training. It has been demonstrated that fixing the final layer, that is also the most expensive in terms of training, does not produce any improvement in complexity, nor, of course, but does not provide any decrease of performance. So based on that, what we do is we use fixed classifier to have stationary features. So that means that since the relationships between the prototypes of the final layer, the WI, and the features, the F, is what you read here, is just a product of the two. Well, if you fix the W, what you do is to force the F, the features, to align toward the prototypes. So in other words, you fix the direction in the space and in the representation space, and you force the features to align to these representations. Here you have an idea, graphic idea of what happens. On the top, you see what happens if you have no stationarity, no fixed classifier. You know, adding one new class changes the configuration. Two classes change the configuration again. On the bottom, you see what happens if you have fixed classifiers. You add the new classes, the other class configuration remains stable. So we use this property to allow compatibility. And particularly, before going in detail, let's understand how can we appropriately fix these prototypes. The idea is to fix prototypes so that the configuration space is equally divided among the classes. And this equal division of the representation space is obtained through the regular polytopes, so-called, that are a generalization of regular polygons or polyhedra in the space. So in other words, the so-called Platonic solid. If we put the prototypes at the vertices of these Platonic solids, well, then you have in equal space the division of the representation space. You have here the rules according to which these polytopes can be built. In one dimension, you have only one polytop. In two dimensions, you have infinite polytopes. They are all the regular polygons. In three dimensions, you have 5. In 4 dimensions, 6. And more than 4 dimensions, you only have 3 polytopes that are those depicted in this picture. You know, the so-called D simplex, D cube, and D orthoplex. And there is, of course, a relationship between the dimension and the number of classes that you can represent in this dimension that are displayed in the bottom of this slide. Okay, without going in detail on that, what is important is that if we fix the the prototypes in the classifier, well, we have, you know, at least the most reasonable division of the space, of the representation space, so that all the classes are equally distinct. Well, let's go to how we exploit this property for compatibility. Well, the idea is, you know, let's use a dimension of the space, the number of classes, pre-allocated, much more than they are, so that we have, let's say, free space for new classes available. Once we have these pre-allocated classes, well, we have an initial set of classes that is used for the initial training, the T-old that you see here. Then if we suppose that another set of classes is added to the former one, we obtain you know, a new set for training, that is the T-new. So, and so on. If we add new classes, you know, T-new grows. So if we use as a check for the compatibility of two representations, the one depicted here in particular, let's suppose to have a verification problem, you know, the M matrix that you see here, and you have a query. If you represent the query with the new model, the one which is updated with T-new, and you use as a representation of the gallery set, the phi-old, then we expect that the updated representation of the query provides a better verification or identification than you know, the model that used the old representation for both the query and the gallery. So in other words, making training with the updated representation, you know, provides a better performance than the old one. This is empirically verified. And in the next slide, which is also the last of the presentation, we use this compatibility matrix just to let you know the performance you get. In particular, consider the new model, the one obtained with the updated representation that we use for the query, for you know, the rows of this matrix. And the old model, the initial one, used for the gallery, the columns of this matrix. Well, if we have position 1-to-1, that means that you use both the old representation and the new representation the same. So it's like a self-test. Then if we instead use as a new model the updated representation, the step, with the one, that means we use the one for the gallery and the updated for the query. Then if we add again another set of data, then we use step 3, so as a new model for the query, and step 1 for the only for the gallery. So we expect, according to what we have said before, that as we improve the representation of the query, the performance is better. So we expect that performance figures in the column are all higher than the performance figure in the very top of the column, which is the self-test, where you use only the very old representation for both the query and the gallery. So if we look at these matrices, you see that this is a comparison between the system that use the fixed classifier and a different system that has been recently released by Amazon. Well, you see that looking at these numbers, you see that the number on the very top, the diagonal of this matrix, oh, sorry. The number on the very top is the lower of those in the column, except for the red squares, where evidently the system is not so good in performing the updated representation. So you see that in most of the case, this technique provides improvement in the identification retrieval performance. So this is the last slide of the presentation. Our idea is that this compatible representation is a big problem in visual retrieval and more in general in tasks like recognition and identification. And one good solution is to exploit properties of fixed classifiers, to achieve a good compatible performance. That's all.
Thanks, Alberto.
Thank you.
So probably it's good to have the questions at the end of the presentation. So I will give the floor to Case now.
Okay, let me share my screen. I think you see the wrong one.
We see it, but it's the scale is wrong.
Hold on. I'm back in the office today since a long while. So I have to get used to my original office setup again, it seems. This should fix it. There we go.
Yes.
You see my screen correct now, right?
Yes.
Okay, so thanks a lot, Nico, for having me here today. It's very good to see old friends again after a long while. I hope we can soon meet again in person. I want to talk about what I call real-world learning, and it's more sort of like as a starting point of a discussion, because the thoughts are not yet completely finalized here. So let me start with awesome learning. So, I mean, the progress of machine learning and artificial intelligence in the last few years have really been mind-blowing. Here is just a sample of some recent covers of Nature and Science, highlighting really huge achievements of people active in the field. I think we all know them. I mean, beating the Go Grandmaster, demonstrating the ability of AI to beat radiologists, playing Atari games, and more recently protein folding, chip floor planning, and what have we. So it is truly amazing. So what else can we wish for, one could say. Well, so in my field, my background is mostly video and image analysis. And what we then notice is that, yes, AI and machine learning is awesome, but many of the state-of-the-art algorithms perform really well when there is sort of like this closed world assumption, where training and test distributions are very similar, and the amount of training data and label data is huge. And as soon as those IID conditions are broken to some extent, machine learning and especially deep learning becomes brittle. And this is especially hurting real world situations where you cannot expect that the test condition and deployment time will be similar to what you have seen during training. Now, of course, the field continues as we should be. And what we have been noticing is that, yes, we're moving to more real world scenarios, but still the state of affairs is to depend on a huge amount of labeled data to get there. Now, so my point is that deep learning and representation learning in general is heavily biased, and towards these training conditions becomes brittle under the real world situations that differ from those perceived during learning. And this is especially hurting when the data is different, the labels are different, the task objectives are different, and fairness all of a sudden comes into play. So I will argue that moving into this corner of the diagram is a dead end. So, I mean, this is a tactic by simply scaling up, and big tech and big states follow this approach, but it's intellectually very displeasing. Not to mention the compute, storage, and ethical expenses of moving in this direction. Moreover, humans are easily able to generalize robustly in a data efficient fashion. So I think there is there must be another way. And there is another way, and there are examples in the literature of people working on different aspects of this problem. So first is what I call distribution gap, and many existing works attack this distribution gap, mostly with methods related to domain adaptation. Another version is domain generalization, and here I highlight a picture from one of the recent papers from my team. In domain generalization, you don't have access to the target domain data, so you only have access to labeled source domains, and you don't know what your target domain at this time will look like. So in the example here, you have access to photos, art paintings, and cartoons, and at test time you will see for the first time in your life a sketch, and the goal is still being able to classify the elephant or the guitar. So this is one aspect of the problem, but there is a limitation in existing works on this that address this topic, because they always assume that the label set is shared across domains, and moreover that a huge amount of labels are available at training time. So another important gap that we need to bridge is the label gap. And this has to do with how can we learn with less labels. So many works have appeared recently, most notably self-supervised learning, self-training, N-shot learning, zero-shot learning, and also open set learning. So how can we learn to expand the label vocabulary at deployment time? Now, these methods are typically studied in without distribution shift. So there are only very few papers that attack both distribution shift and the label gap. So I think that is an opportunity. Then the third one is an objectives gap. So this relates in a bit to what Alberto was saying. So here we do not only want to optimize a representation for a single task, but essentially it should be able to address multiple tasks. And this is actively studied in continual learning. So where you adapt your classifier to changing tasks and changing environments. Again, here we have seen this is an upcoming topic. Many new approaches are being proposed. I did not see many approaches yet that also consider continual learning under distribution shift and changing labels. So there is an opportunity there too. And then the fourth one is the fairness gap. So fairness has been discussed by many. It is important to incorporate fairness before you start with representation learning by creating the appropriate sets of data that are, at least the biases are known, or to do it after the fact to correct for biases. But I think as a community who works on representation learning, we have the moral obligation to also take fairness into account during the development of our algorithms, and that is feasible. So many algorithms actually amplify biases that exist in data sets. So we should be at least be able to identify these amplifications and address them. And there are several works in the literature. We have work under submission as well that can address this fairness gap to some extent. So we have these different gaps, but they are so far mostly addressed individually. So we have been seeing some papers that do few-shot learning across domains, but this is really upcoming topic. We have not seen it in continual learning or even addressing fairness in the mix as well. So my point is that no learning methodology exists that dynamically generalizes and adapts across domains, labels, tasks, and fairness simultaneously. And I believe this should be the objective or the ambitious long-term goal of what I call real-world learning. And with that, I would like to stop and open the discussion once the next speaker is done. Thank you.
Thank you, Kees. Radu?
Yes, thank you. So I'll start by sharing my screen. So let me know if you can
Yes.
see my screen. Great. So thank you for the invitation to the panel. So what I wanted to talk about today is green AI and finding new forms of learning for what I think is very important for the next steps in AI. So just to give you a brief introduction where this comes from. So over the past few years, handcrafted models for various machine learning tasks have been replaced by these trainable models that are known as deep learning. And essentially, this was caused by the superior performance of these deep learning models. So, okay, so the main driver for the performance improvements are the progressively deeper models and also the increasingly larger data sets. And I think, well, there is also the higher computational power that we have access to at the moment. But I think maybe because we have this so much power available, people have also tried to use deeper models and use larger data sets. So while this generated the progress in AI, we are still training neural networks with procedures that were invented a long time ago, such as, I don't know, some variant of stochastic gradient descent. And we are still using paradigms, learning paradigms that require a lot of training data. So there is supervised learning that we know, for example, if you want to train a state-of-the-art object detector, you need to use ImageNet. But people have started showing that you can train even more powerful models through self-supervised learning. So you don't need the ground truth labels from annotators, but still this gives you the means to include even more data into the training. So this makes things even more computationally intensive. So I think the problem that we need to solve is to be able to train models more efficiently. So the moment we know that convergence is very hard to do. So there are a lot of researchers that try to train models to, and they do not always reach convergence. There are a lot of problems. So actually the training process requires a lot of babysitting. So actually this adds to the actual training process that is going on. So it's not just that you start training the network and you measure the time until the end, but it's also the tries that you do until you find the right way to train that model. So the overall process is very inefficient, and there are some papers on green AI that discuss this problem, and they even go towards estimating the greenhouse gas emissions by some of these state-of-the-art models. So for example, the state-of-the-art model in NLP, BERT, is a transformer model that generates, so in order to train this model, it generates about the same amount of CO2 emissions as 5 cars during their entire lifespan, which is about 10 years. So that seems like a lot of emissions that can cause negative impact for our environment. So yeah, what I wanted to raise the awareness about today is to try to develop new forms of learning and more efficient neural models that try to be green. So I think that this can be done by considering to optimize the components that go in the development of machine learning models or deep learning models, so optimizing them towards efficiency. So I think these components are the neural architectures. So here we have some papers and actually a lot of works that try to look into more efficient neural networks or different learning paradigms, or try to find better optimizers. But I think that these need to be studied jointly and maybe find better mixtures of all these components. So here I'm just suggesting some ideas. For example, in terms of learning paradigms, I think knowledge distillation and teacher-student training could be a way to go, but it still requires you to have a large model that is, so you can distill the knowledge from a larger model, but in order to train that model, you still not need a lot of training time. So maybe it's not the best way to do it. Another way to train more efficient model is curriculum learning, which I explored a lot in my recent research. And of course, we can also think about different optimizers. Okay, so in the end, what we want to achieve is to reduce significantly the CO2 emissions. And this will also enable us, so if we have more efficient models, we can also have applications of deep learning in scenarios which are not previously possible due to the high computational costs. So for example, applications that require real-time processing or systems that need to be deployed on embedded devices and so on. So yeah, I think yeah, these two benefits will have a positive impact in all areas where machine learning is currently used. So yeah, this was my last slide. So I tried to keep it short so we have enough time for discussion.
Okay, thanks everyone. So I want to invite the people in the audience, if you want to put a question, just raise your hand, and I think it's I think it would be I think our panelists gave us a lot of nice ideas to discuss. I see that Yanis has booked a question, but let me start making a comment first, which I think one of the, if I would find a common thread through all the presentation, I think this is something that Alberto was bringing in. It's a compatibility, and I was wondering, Alberto was addressing the feature compatibility, but I was wondering if we can extend this concept to, let's say, different modalities on one hand. So if I have now a feature from, I don't know, audio, can it be made compatible with, let's say, what I have from visual information? And also addressing to what Radu was presenting, I was wondering if you can consider some kind of model compatibility in that case. So now going even to more abstract. So now if I'm getting some new learning method or a new learning model, can I just reuse what I had before? Because that would reduce also my my time, my emissions, and everything. So Alberto, what do you think about trying to extend it to, let's say, instead of class compatibility, we extend it to multimodal compatibility?
Yeah, I think that there is a paper by Amazon Research, particularly if I remember, it's by Yantao Shen, and Stefano Soato is one of the authors, that particularly addresses this, this problem you mentioned. And in their research, you know, that is that BCT system that we have compared with in the very last slide of my presentation. Well, that system exactly addressed the problem of compatibility between different architectures, for example, different networks that provide different outputs. You know, the way in which they deal with that is a little bit trivial, but, you know, they address that problem and provide some evidence it can be done.
Okay. Radu, what do you think about kind of, let's say, model compatibility in some sense? And you already have it in, let's say, in the distillation discussion, but maybe we can extend it a little bit.
Yeah, so I think this is an interesting topic to discuss. I'm trying to think of maybe a way that this could bring perhaps more efficient models. I'm not sure if this can be achieved. So maybe, yeah, this can be I'm thinking that this could help in transfer learning, for example. If we have a better model compatibility, then I think maybe we can transfer models to different domains and even different modalities better than what we currently have. So yeah, this will definitely help us reduce, I think, the training time from these models that are trained from scratch.
Okay.
Yeah, so I think, yeah, this is a important thing to achieve, if
sure, if possible, of course.
Yeah.
So, Case, just a curiosity, what about extending this compatibility also to, let's say, end user compatibilities? I'm thinking about some kind of, let's say, societal compatibility, if you really want.
So let me first say another thing. So I think that adaptability is
it's the way to go. Yes,
is the key here. And what I think that we need to do is move away from having a clear definition of what is our train set, what is our test set, and what is our label vocabulary. Essentially, that is solved. Deep learning has solved that problem to an extent that it is sort of good enough. It's not really interesting anymore. There is work from folks at Berkeley, at least 2 sets of papers on using information of your test set without using the label information, of course, but using the time you see a batch of test samples and use it to adapt your training classifier. And I think that is a very intriguing way of looking at many of our learning problems. And I find it very, very interesting topic. And so, and of course, yeah, you can do the adaptation at the feature level, at the classifier level, at the model level. I think that's all open territory waiting to be explored.
I agree. I mean, I think using context, if you want, in more some sense, using context from your test domain, and you do have a lot of information, can really help a lot, of course.
Yeah,
I agree. Okay, so Yanis.
Yes, thank you, Nico, for the organization and the panelists for the very interesting talks. My question is yes, mostly for Kees. Thank you very much for this very interesting approach. An obvious question is which directions could be used for this real world learning, which incorporates all these aspects that you mentioned?
Yeah, good question, Yannis. I think I'm going to start attacking this problem based on my expertise in video. So I think video is a very rich modality that offers us the opportunity to attack this problem. So it is multimodal, it is spatiotemporal, it's causal, and it has a huge variety of tasks that you can execute. And at the same time, it is also the modality where it is super clear that keeping on labeling and collecting huge amounts of data is not the way forward. So I think that is a very good modality to study the problem of real-world learning. And then in terms of approaches, I think meta-learning is a very powerful paradigm, not only in domain adaptation and generalization, but also in few-shot learning. And also continual learning is a very interesting emerging theme. So on the crossroads of meta-learning and continual learning, as well as using self-training and self-supervision in a smart way and correspondence between modalities and spatiotemporal correspondence, I think that mix should provide a really fruitful starting point.
Thank you very much. It's very exciting.
I expected, Case, that you said, you take the paper and said, we already have it. Here it is.
Unfortunately, no.
Yes, I know.
But one may dream, right?
Yes, of course. Niccolo?
Oh, yeah, thanks. Yeah, I was also sort of it's more a comment than a question. I like Case approach. And as some of you may know, I've been working on online learning for a long time. And I like a lot the approach of trying to combine robustness to different aspects, like ability of address shifts in distributions, address different tasks, as in meta learning, or address the partial availability of labels. These are all things that have been studied within this online learning scenario. And what I've learned in doing this research is that oftentimes if you start from simple algorithms, is very easy and convenient to grow the algorithm by adding and combining different properties. So in some sense, there's a pressure towards simplicity, because somehow you would like to start with something simple and then make it robust to different things simultaneously. And if you start with something which is already overly complicated, that you are basically doomed, because you cannot control the different variables. So this is something that this is sort of a pressure towards simplicity is something I like a lot. And online learning somehow is providing this. It has a robustness to shifts in distributions built in, because there's no distribution to start from. And it has some of these meta learning, multitask and partial feedback kind of properties. On the other hand, is a very bare-bone and simple environment, so it might not be able to achieve the kind of performance that you have with more complicated tools. So there may be some kind of middle ground there that can be get. Okay, so another comment I wanted to make is that this idea of taking a peek at the test set, excluding labels, of course. It has a name. It's called the transductive learning, and it was introduced by Vapnik in the 90s. And this is, Vapnik introduces it as a purely theoretical framework in which you're sort of bridging the extending, if you like, the standard batch learning viewpoint, in which you have a training set and then a completely unknown test set, which is drawn from some distribution. So there's a bunch of results that go under the name of transactive learning, and so you guys, if you guys are interested in that, you may take a look at those. Okay, that's all. No questions, but just comments.
Great, thank you, Nicolo.
Thanks. Akis?
Yeah, thank you. Really exciting discussions. I have a kind of practical question on how we evaluate real-world learning systems. Because in practice, we will have to, reserve some data sets to be completely unknown to the learning system, and then say that, okay, we have completely independent data sets, new classes, new domains, and our system did well on this. But how can we be sure that when we add a new, completely unknown data set, that the real-world learning system will indeed perform equally well? Is there any consensus in the community about how to do a proper evaluation of real-world learning systems?
Well, Alberto, it seems to be kind of skeptical, but
I don't know. You see my face.
yeah.
I don't know. It's a hard question to answer.
Well, actually, it's not, Alberto. If you think about it, the end user is happy, then you evaluate it. I mean, of course, this is not an objective way of doing it, but as long as it solves the problem.
Probably
then,
you can evaluate in terms of anomaly detection, but I don't know. I don't know. I don't know. Kes probably has.
No, he doesn't.
Give the ball.
It is an open question. The answer is not there yet. So you can essentially propose a benchmark and write a paper. There is a work from Stanford, I think it's called the WILDS benchmark, where they do a lot of cross-domain evaluations. So that is a good way to measure robustness by testing it on multiple test collections at the same time. So, I mean, of course, yeah, you can always find another test domain where it will break, but that is a good start, so that at least will help to cover the generalization and distribution shift robustness. So there are a few early papers on attacking this theme. I mean, maybe you have also heard about the foundational model paper from Stanford. I almost finished reading it. It's about 160 pages or so. But there they also address evaluation, how to do this moving forward. So it is, people are thinking about it. There is no definite answer yet.
Okay, just wanted to make sure I didn't miss something really important. Thanks.
Yeah, so can I also add that maybe it is important to discuss the validation set. So when you train your model, you also need a different test set that you can tune your hyperparameters. So if you do this on the test set, then you can do overfitting in hyperparameter space. So like you're overfitting the hyperparameters to your test data. So just make sure that you have the different test set when you optimize the hyperparameters of your model, and then you just apply the model on the final test set. And another thing maybe is to try different test sets to evaluate your model. So because I think overfitting is very easy to do, where you think you will obtain some improvement, but it's not applicable to other test data. So yeah, it's complicated. It's not an easy answer, but there are some best practices ideas that I try to share.
Okay, Yanis?
My question is regarding the feasibility of our approaches, because so far all we discussed here, it's mostly data-driven learning. But if we really want to address real-world problems, then we need abstraction.
Yeah.
Is it sufficient? Of course, you know, the basis of our brain is neurons, so it's electrical signals, so we can claim that we can work this way. But at a higher level, our brain works with abstraction and concepts. So should we really move towards something that's hybrid, that has both concept creation, for example, through clustering, and then some combination with symbolic AI?
Well, let me make a comment on this first. I mean, I completely agree. I think it's that would be the way to go. And I think one of the things that we don't use it very well, it's somehow that the humans do, it's kind of using experience, right? So we've seen many things and we put them together and we are able to extrapolate and so on. So the mind generalization is going into this direction. But what I believe our methods nowadays, I mean, we kind of keep on relearning everything from, maybe not from scratch, but anyway, from very, very low, instead of kind of trying to be able to benefit, to kind of build on top of each other, whatever, in some sense. Okay, so I think that's that will be something that we need to move on. I don't know if you guys have opinions.
Would be not easy to do.
Of course.
It's true. It's not easy to do. That's for sure. My remark has also a societal aspect. If you see the growth of data and information, this is exponential. If you see the growth of knowledge, it's linear. Yeah. So essentially, you can think abstraction as a data compression mechanism as well. And humanity can cope with linear increase of knowledge. After all, you know, the population increases at a linear growth rate, more or less. But we cannot really cope with handling with data at an that are created at an exponential rate. It's a lost battle.
Yes, yes. Of course. I very much agree, actually. So. I mean, the success of deep learning is essentially injecting knowledge by labels and coming up with clever inductive biases in the architectures. If we want to now reduce the number of knowledge, so the number of labels, the knowledge has to come from elsewhere. So I very much believe in such a hybrid approach. And there's actually very interesting work on causality and how to incorporate that in learning formalisms, and also hyperbolic representations that allow to include ontologies and knowledge graphs inside the representation learning. So there is some approach, some work happening, and I'm not so much a believer in you're either knowledge-based or learning-based. I think very much in the joint forces there is a lot to gain.
But I think the point of Yanis is also that we are still doing a lot of pattern recognition, okay? But still patterns are fine, of course, and we understand all these things, but we know much more than patterns right now, okay? So we do have a lot of semantics, a lot of things that are more abstract in some way. Right, because if we learn patterns, well, it can be anything. You know, patterns in general are kind of agnostic in some way. Not always, of course, but you can have some knowledge and so on. But we do, as humans, I mean, as population, as society, if you want, we do have these abstractions. And if we can benefit from this, then it would be definitely something very useful.
There's also another point that we have done some research, and we would like to have cooperation with any of you. I believe in what I would call knowledge education, which is an extension of knowledge transfer and also of federated learning. There's no need to do the same thing all over the world. We can have teacher networks that can teach student networks, and student networks can try to find the best teacher, and so you can have a distributed environment that can be used to transfer knowledge from one node to the other one in the best possible way, either in a cooperative way or on a competitive way as well, because you know, for example, companies compete with each other. I can be much more concrete on this. So if there is any room for cooperation in the framework of ICT 48 projects or beyond this, then we have some means also in AA for media to have such types of cooperations.
Mm-hmm. Okay, let's see, Yanis, let's try with to conclude.
Yes, just wanted to say something, a comment in the previous discussion regarding the fusion, the hybrid approach between learning and knowledge base. My thought is that this is not something new as an idea. It has been proposed and discussed, and it always comes as an additional idea for many, many years now. And of course, there have been also papers and more white papers and so on. And but it seems that it's not there yet. So my feeling is that there must be some kind of fundamental difficulty, some kind of problem, a real important challenge there that makes it difficult to have such a hybrid approach in full scale, solving practical problems in many domains and so on. So yes, just this feeling that I would like to
No, I agree. I mean, just to come up to what Kate was doing, I think there is a gap in there somehow. And I mean, these guys from the semantic web, whatever, I think they, as you said, they try to do things and so on, but I believe they are solving toy problems or problems where the context or where the rules are very clear. But if you go to some sort of, let's say, problem that we are solving in computer vision, where everything is noisy, you have high dimension and so on, these kind of things, they don't scale. I think that's the main problem that we are facing. But I think it's I really appreciate the approach of Case of defining gaps, and that's in line of, let's say, the school of, I would call it the school from University of Amsterdam. I mean, Arnold was the one kind of, you know, bringing in gaps and so on. So I think it's good to continue in this direction.
Before we finish, I would like to remind you that if it is possible for you to define some open issues that can be useful for PhD students to fine-tune their research, please do so.
Okay.
We're going to try to combine them together.
Sure.
Are we done, Nico?
Yes, I think we are done. Okay, I think
then we have a break now, a coffee break, and we start again at 11:45. So let's say in how many?
20 minutes.
20 minutes from now. Yeah. Okay.
Thanks a lot to everyone.
Thank you so much.
I think it was very useful anyway with ideas and everything. Thanks. Appreciate it.